Are you feeling curious?
Yeah!
Today on Curious Crew,
I've got my little DC light going on over here.
get revved up for some powerful investigations,
Surges of energy, this increase and decrease of electricity.
exploring the science behind electric generators.
Wow, that's a lot of energy conversion.
Support for Curious Crew is provided by MSU Federal Credit Union, offering a variety of accounts for children and teens of all ages while teaching lifelong saving habits. More information is available at msufcu.org. By the Consumers Energy Foundation, dedicated to ensuring Michigan residents have access to world-class educational resources. More information is available at consumersenergy.com/foundation. Consumers Energy Foundation, supporting education and building sustainable communities in Michigan's hometowns. And by viewers like you. Thank you.
Hi, I'm Rob Stevenson, and this is
Curious Crew!
Welcome to the show, everybody. We always like to start every episode with a couple of discrepant events because discrepant events stimulate
Curiosity!
That's exactly right, and I've got some fun ones for you. In fact, I even call this one Faraday fun, but we'll talk about that in just one moment. I'd like to direct your attention right over here for just a moment. And Julia, do me a favor. Could you describe for me what that looks like in that little quartz bulb right there?
It looks like if you crushed up black licorice in a grinder.
I love that. Black licorice in a grinder. Well, I'm going to do something that seems a little strange. We're going to actually light this little burner and heat up the whole system. So we want to be careful, right? Safety first, everybody. Let's get these goggles on. And I'm going to light this up. Got a little burner underneath. And once that goes, we're just going to let it be. Oh yeah, that's working. Now, meanwhile, I have a question for you, Victoria. I'd like you to look at this whole arrangement. I've got something set up here and just make some observations. I'm going to have you share your observations in just a moment. But first, I want to tell everybody else about this little device. I don't know if you've ever seen one of these before, but this is a galvanometer. And a galvanometer is really effective at detecting small amounts of current electricity. And now I want to defer back to you. What are you noticing about this whole arrangement over here?
Well, I noticed that there are two wires.
Okay.
And they are both connected to this meter.
Okay.
And then the other string is connected to these two connectors. And they are connected to this battery, and there's a missing connector.
Okay, well, you noticed a lot. Thanks, Victoria. So a couple of important things to be really aware of here. This is called a shackle bolt. And as Victoria described, these two wires are not connected to each other. They're connected to different sides. The other thing to notice is the wire where it contacts the bolt, it's just with the insulation. So we don't have metal on metal. That's kind of important. Now, I have a question for you, Victoria. What do you think will happen if I tap this alligator clip on the battery?
I think what will happen is that the meter will start moving.
Okay, let's take a look. Ooh, that was a really good prediction. So we get a little deflection with that meter. Now, it's not very much, is it? Just a teeny tiny little bit. Now, what do you think will happen if I keep it attached?
Maybe it'll go very far, or it'll go maybe to 10 or 20.
Okay, let's see. I'm gonna hook it right on there. Now that's not very exciting, is it? It just sort of holds steady, which is really strange. It moves when we tap, but then it just holds steady when we just leave it there. Now I want to go back over to this, and I want to see if I can give this a little push. There, it's starting. Julia, what are you noticing there?
I noticed that the back of it has a little light that's flickering in different colors.
It is, and in fact, I'm gonna turn this around so we can see it that way too. There's a little light that's flickering with different colors. And now it almost looks like the colors are, yeah, they're still sort of flickering just a little bit as this is rolling and rolling and rolling. This is my mystery generator. I'm gonna invite a few of you to see if you can reverse engineer this, see if you can explain these phenomena by the end of the show. So who would like to do a little scientific modeling today? Let's see. Okay, Adia, Zana, and Ishan. All right, little modeling moments for them. Now, does anybody have a guess what we're going to be investigating today? What do you guys think? Vinny, what do you think?
If I had to guess, I would probably say generators.
That is an excellent guess. We are investigating electrical generators. Stick around, the crew is going on a power trip.
Let's figure out those discrepant events.
The needle only moved when Dr. Rob tapped the battery, but when he held it still, the needle didn't move.
I know, that power surge must have something to do with the wire on the other side of the bulb.
That engine was pretty cool. I wonder how the heat made the motor move.
Have you ever closely observed a machine running? There is usually an electric motor that uses electrical energy and converts it into mechanical energy to get things to spin. A generator does the exact opposite by converting that mechanical energy into electrical energy. There are different ways to supply energy into a generator, like through burning fuels, but you can also do it with wind, water, steam, or your arm power. Great job!
Now, for us to really understand electrical generators, we need to start understanding electromagnetic induction. Now, that sounds like pretty complicated stuff. It's actually not that complicated, and we've got some devices that can help make sense of it, okay? First thing I want to point out to you is I've got this coil, and there's a lot of wire there, just a lot of wire. It's connected to one end of the wire here and the other end of the wire way down here, and I'm going back to my galvanometer again, okay? I also have this one that has tons and tons of wire, but the interesting thing here is the middle of it has an iron rod. Now, what do you guys think will happen if I connect this to the battery? What will happen?
I think this iron pole might get magnetized.
So I'm gonna disconnect it for a second, because I'd like to just put this inside the larger coil and see if we have any sort of excitement. Not really. Okay, so let's magnetize it, just as you suggested, Ishan, and we can double check to make sure it's magnetized. Oh yeah. Oh yeah, so that's working as an electromagnet now. Okay, I'm gonna place the electromagnet inside and let's see if we get any deflection.
Oh, yeah.
Oh, yes, indeed. Now, what happens when I do it fast?
It goes more.
Goes more. That's kind of interesting. Now, this is all that we mean with electromagnetic induction, okay? If we want electricity to go to the galvanometer, we need a moving magnet to induce the electricity. You saw before, when it was not a magnet, it didn't really do much, did it? Okay, let's try this another way. I have each of you with a little coil loop.
Oh, mine not so little.
Oh yeah, yours is really not. Yours is not that little at all. And I'm actually gonna extend this just a little bit. And do me a favor, could you please connect yours first, Finny? Okay, so you've got yours connected, and this time we're going to use a permanent magnet. This is a cow magnet. And I want to place this inside and see what kind of deflection we get.
Oh, well,
That's not
really
a
little.
Yeah,
Penny.
very little.
Very, very little, even though I was doing it pretty fast. Okay, let's disconnect the little one, and we'll go to Ishan's. His has a few more coils wrapped in there. We can see what sort of effect that makes.
Oh, that's a
A
little
little
better.
bit more
A little bit
Yeah.
more. Why do you think we'd have more?
because
Well,
it has
it's
more
pretty
coils.
thick.
More
It's
coils, thicker.
Yeah.
Okay, so then if we want to see more coils and thicker, maybe we need to talk to
Yeah.
Victoria.
Okay.
Okay, so Victoria has hers ready, and let's see what sort of a deflection we get this time.
Oh, wow. That's a lot bigger.
Okay, so it's not as much as we saw with this, but that makes sense. There's way more
Yeah.
coils there. So if we want to induce electricity, what do we need? We need a moving magnet, right? And if we have more coils, more deflection. If we have more speed in the magnet, more deflection. And that's all that we mean with electromagnetic induction, but it's the primary principle in electric generators.
In the early 1830s, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. We saw how the galvanometer reacted when the magnet moved into the coil of wire. But what if we moved a wire through a magnetic field? If we had a large horseshoe magnet and moved a straight wire connected to a galvanometer into the magnet, we could see a reaction. Generators need wires, magnets, and motion to make electricity.
So the interesting thing about electrical generators, it's all about energy conversion. Now we've got some mechanical lights and you each have one. Sarah, can you demonstrate yours and then tell us how it's working there? That's loud.
It's really loud.
So what do you think's going on with yours?
I think there's a motor producing energy into the light.
Okay, a motor, and you're actually spinning that whole thing. Nice job. It's kind of interesting. We can get electrical energy coming out of a motor one way, or we can have mechanical energy coming out of a motor the other way. It all depends on the direction that we're talking about. Thank you so much. Isaac, how does yours work?
When I squeeze the handle, it moves the magnet, which is in between two wires, creating energy.
Okay, and so we've got a moving magnet that's inside the wires. Do you think you have a moving magnet and wires in yours? Mm-hmm. Yes, indeed. Now yours, Anna, is kind of interesting. How does yours work?
You have to shake it up and down.
Shake it up and down. And why do you think we have to shake it up and down?
Because the magnet is moving up and down with the movements.
Okay, can I see that for just one second?
Going through wires.
Okay, so we actually have a moving magnet that is sliding back and forth between the wires, and so it requires us to shake it so we can get that induced electrical charge. Now, the interesting thing about a shakeable light like this, there's even a little capacitor in there, so the more you shake it, it will store some of the energy. Otherwise, you'd be walking along like this all the time, which would be a little ridiculous, wouldn't it? Okay, let me show you this. This is my handy power. And all of yours have something in common. All of yours have a moving magnet inside wires. Look at mine. I have moving wires inside a magnet. Either way can induce electricity. Now, when I spin this, we can get that coil turning, and you'll notice we've got a permanent magnet up on top, and that magnetizes the sides. This is called the armature. And once this whole thing is magnetized and we get a moving wire, we get electricity going out. And I can have DC current or AC current. I'll show you the DC. The DC is pretty easy to see. We've got a split ring on the front with these little brushes, and I'm gonna show that real quick. So now I've got my little DC light going on over here. Now, if I want AC, I'm gonna have to turn this sideways. The AC output has a little slip ring on this side with the brushes. I can switch this over to AC, and now my little AC light turns. But this actually doesn't turn very much. I want you to see, it's not very bright, a little bit of a flicker. Hey, did your lights flicker when you guys did that?
Mm-hmm. Yeah. Mm-hmm.
Why do you think it would do that?
Because I think there's probably surges of energy going into the light.
Oh, surges of energy, that's right, this increase and decrease of electricity. All right, let's everybody do yours. You try it. I'm gonna put it on DC. Everybody demonstrate them. Oh yeah, excellent. Well done, crew. You three really light up my life.
The crew discovered that they could convert mechanical energy into electrical energy in a generator, and they used arm power to get the rotor to spin. There are other ways to get the rotor to spin too. These include water wheels, windmills, or steam that blows against vanes causing a turbine to rotate. When you can connect wires, magnets, and motion, you've got a generator. What a dynamo!
So have you been having fun investigating electric generators today?
Yeah!
I'm so glad. I've got a fun STEM challenge for you. You're going to make your own simple electric generator. And Finney, I got a question. What might we need to make a generator?
I think we might need some wires and maybe some moving magnets.
There we go. I think you're ready to start your build. Let's do it, you guys.
Put the nail in. Step one.
So we should do 100, 100, 100.
Yeah, we're doing 100,
and then we're gonna do it like that, okay.
The materials we are using are wire, nails, magnet, and a tiny little box.
The most challenging part of the experiment was definitely trying to figure out who was going to do what.
All right, here, I'll hold this thing.
Yes, that would be actually very helpful.
Don't go too fast. You can take your time.
Finny was holding the coil. I was wrapping it all around. Xana, she was taking count of the numbers.
7, 68.
It took a while. We had to do 200 on each thing.
61, 62, 63, 64.
83, 84, 85, 86, 87.
We should probably do 200.
I think 150.
You're going to be doing this
How about 175? It's in the middle.
Yeah.
Okay.
We wrapped the wire around 175 times each.
99. 100.
100. Okay, 200.
Wait, let me cut the length.
Yep, cut it.
I'm learning that cooperation is definitely key when doing experiments.
Okay.
All right, don't move it now. Don't move the nail.
The most challenging part of this experiment was trying to drop the magnets in without them like clicking together.
Alright, just a little bit.
The magnets aren't equal.
Our arms were getting pretty tired, and some of the coil was starting to unravel.
200.
200.
So this looks great. I see some interesting little apparati here, some electrical generators. Are you ready to test them?
Yeah.
I thought you might. Now, I saw some of you spinning your nails like mad and using the multimeter to see if you have some current that you could detect. Now, that was probably pretty tiring, wasn't it, spinning it by hand?
Yeah.
We're going to use this method. And in fact, we're going to test each one of these. And I want to start with your table. We've got the end of the nail now in the drill, and I think Sarah's going to show us. But first, how many windings did your team use in your generator?
200.
On each side?
Yeah.
Oh my gosh, okay. Let's see how it works.
Wow.
Oh, very good. I think this table is next. So we have the drill set here. Finny, how many windings did your team use?
We used 200.
200, the magic number. Okay, let's see how it works. Wow. That was nice and bright. Well done. We have one more to test. So our final table. Isaac, how many windings did your team use?
175 on both sides.
Oh, excellent. 175 on both sides, so a little bit different. Okay, let's see how yours works. Oh, yes, well done. So we've got 175 windings on both sides there, 200 windings over here. What would happen if we had even more windings?
More energy.
Yeah, more energy. It's going to be brighter, more current. Excellent. Now, all we needed is that moving magnet inside that coil of wire, and you can try making your own simple electric generator. Crew, more power to you.
The crew made generators out of small cardboard boxes, but you can easily make one out of a small craft motor. By connecting the leads to a small LED, you can rotate the small shaft of the motor to produce electricity. Motors are designed to convert electrical energy into mechanical energy, causing the axle to rotate. But if the energy goes the other direction, the mechanical energy becomes electrical energy, and that is a generator.
So as we've been investigating electrical generators today, there's been some commonalities. There's always magnets, and usually the magnets are moving, and there's wire, and that's going to be inducing electricity. And most of the time, we've been using our hand power to make things work.
Yeah.
But generators can also be powered other ways. Here's a good example. What is this here, Jackson?
A wind turbine, it looks like
A wind turbine, that's exactly right. Have you seen wind turbines, Jackson?
Yeah.
And what do you think they're for?
Maybe creating electricity.
There you go, generating electricity. So it fits well into our theme today. So let's think about how it actually works. Adi, I want you to think about that. How does the windmill actually work?
The wind's pushing against the sails to make it turn.
So if I were to swing this around simulating the job of the air particles, we might see an effect. And Julia, I'm gonna ask you to watch closely because we're gonna try this. So what are you noticing, Julia?
I noticed that the gears are, these two gears are spinning each other, and it's lighting up this light.
You're noticing a lot. So of course, the gears are often hidden in those big wind turbines, right? You can see that big tube behind the sails, and you don't really know what's going on in there, but this gives us a good indication. We've got gears in there, and it's sending out electricity. Now ours, we can see the little light turn on. But when it's out in someone's farm, for example, they're actually putting electricity back into the grid. They're contributing to our electricity, which is pretty exciting. and a great natural resource here. I love that. I want to direct your attention down to this. We can often generate electricity using steam. Let's explain how this works. This little boiler, we put water inside, you pull this little plug and you pour some water in there, and then you light the little burner, and eventually steam comes out, travels down these tubes, and then they'll start coming out through these little pistons, these little veins in the pistons, which gets them turning. Now, once we have it turning, we can guess what might be in here. What's in here, Jackson?
Maybe some moving magnets and wires.
Oh, what a good thought. If we're talking electrical generators, we do in fact have a moving magnet inside a coil of wire, and that is going to get connected to the light bulb. And if I spin it fast enough, we can even see that light turn on. Isn't that amazing? Now I'm still cheating, still using mechanical energy with both of these, but normally we have wind that can do the work. We've got water that can do the work, with a lot of energy conversion in this one too, from chemical energy to kinetic energy with those particles moving, to mechanical energy with the pistons moving, and finally to electrical energy. Wow, that's pretty impressive. Crew, did you get a charge out of this?
Yeah.
So did I.
We've explored how generators convert different kinds of energy into electrical energy, but did you know engineers are creating wearable generators? It's true. These small devices can be worn as a ring, bracelet, or other jewelry that directly contacts your skin. These thermoelectric generators convert the heat from your body into small amounts of electricity. So someday, we will be providing the power to charge our watches and phones. Perhaps you will help develop these technologies. Here's to the power generation.
So we know that a magnetic field makes an electric current.
Right, and Dr. Rob was making an electromagnet when he connected the battery to the bolt.
But remember, in the power loops investigation, the meter's needle only moved when the magnet was moving.
The magnet moved in the wire coils and the mechanical lights too.
And those were hand-powered, moving the magnets, while the engine did it by heated air, moving the piston.
So have you had fun investigating electrical generators today?
Yeah!
That's excellent. It's now time to return to these discrepant events because I know they sparked your interest before. So what have we figured out about the Faraday fun here, Adia?
Well, the battery that's connected, the electricity magnetizes the bolt. That's what starts a current on the other side.
And the needle on the meter only moves when the current starts and stops.
Excellent. Very good thinking, everybody. So we saw that when we tap right on this, we suddenly have this bolt become a giant electromagnet. Even though these wires aren't touching, it induces an electrical current on this side, which we see as a deflection on the needle. Now, the interesting thing, and just exactly as you said, Ishan, we see when it starts and stops. But when we keep it on there consistently, the current's steady and we don't really see any change. We're actually recreating an experiment that Michael Faraday did back in 1831. He not only realized you can turn on and off an electromagnet, but he also realized that a moving magnet induces electricity. Pretty cool. That's what led to electrical generators. Now, how about this mystery generator? What have we figured out here, Xana?
The wire in the tube heats up the air and the air particles hit the piston.
And the piston turns the axle and the rotor to generate electricity.
Excellent. So we have a lot of energy conversion going on right here. First of all, we started with the little burner, which is chemical energy. Then it heats up the wire and the air particles, as Xana talked about, which is kinetic energy. And then those particles hit the piston and move the axle and the rotor, mechanical energy, as Ishan was talking about. And finally, it can activate the motor, where we have it converted into electrical energy. And we saw that beautiful color change because all of that depended upon the amount of current coming through the LED. Wow, that's a lot of energy conversion. Crew, thank you so much for shedding some light on electrical generators and for reminding us that knowledge is power. So remember, my friends, stay curious and keep experimenting.
Get your Curiosity Guide and see more programs at WKAR.org.
Support for Curious Crew is provided by MSU Federal Credit Union, offering a variety of accounts for children and teens of all ages while teaching lifelong saving habits. More information is available at msufcu.org. By the Consumers Energy Foundation, dedicated to ensuring Michigan residents have access to world-class educational resources. More information is available at consumersenergy.com/foundation. Consumers Energy Foundation, supporting education and building sustainable communities in Michigan's hometowns. And by viewers like you. Thank you.
I'm gonna say I know these described events sparked your interest.
Smiling.
Yeah. Your hand tired yet?
A little bit.
The meters need to only move.
I knew these. I'm gonna try that again. That might make it to the end of the blooper reel.